So am I audible to all of you? So am I audible to all of you? Am I audible to all of you?
Yes, sir.
Ansari, are you there? Ansari?
Yes, sir. Hello.
Oh,
Yes,
you
sir.
just asked me a doubt a few days back, right? When I was not well on that time. During that time, I was a bit ill. So, what was your doubt at that day? Can you tell me?
Sir, about the shear force and bending moment diagram.
Acha, just ask me your doubt, or if you want to draw any diagram and ask, you can share, draw it. I can allow you that thing also. I was not well at that time. I'm so sorry for that.
Sir, I will ask later, sir.
You can ask me.
Sir, I will ask later, not now,
Why?
sir.
You can ask right now. No problem. I'll just do a doubt clearance session and then we'll just go back to our portion classes. No problem with that.
Doubt to পিছত clear কৰি লওঁ, sir. এতিয়া
কিয় কি
নাই,
হৈছে?
sir. ঘৰত নাই, sir.
প্ৰব্লেমটো কি?
Sir, I'm not in home, sir.
You are not in home. ক'ত আছা ক্লাছ কৰিবলৈ?
Yes, sir. মই অলপ বাহিৰত আহিছোঁ, sir. এতিয়া rain হৈ আছে, sir.
আচ্ছা ঠিক আছে। What about others? Do you have any doubts regarding the previous classes? I just wanted to know that. You didn't ask me any doubts. Like only one or two people asked me doubts. Other than that, none of you asked me doubt. So like I'm asking every one of you today. Please be attentive. Just ask me any doubt or something like that if you have. Yeah. Any one of you, even if you don't have, you just say me you don't have, now. If you don't have any doubts, just say me you don't have doubts. Because you have like your exams in the last week of this month, I think so, if I am not wrong. Yeah, please, someone. If you don't have doubt also, you just say me that you don't have any doubts. So no doubt, any one of you? I can't wait for so long now. Okay, then if you are not having any doubts, let me start the topic. This is called flexural stresses today. So before that, I'll just show you some tutorials. So this is the flexural stress, what is meant by it, and what are the different types of something like that. Okay.
If we apply a load to a beam, it will deform by bending. This generates internal stresses, which can be represented by a shear force acting in the vertical direction and a bending moment. The shear force is the resultant of vertical shear stresses, which act parallel to the cross section, and the bending moment is the resultant of normal stresses, called bending stresses, which act perpendicular to the cross section. It's important to have a good understanding of these stresses because any design or analysis of a beam will involve calculating them. Let's look at bending stresses first. To keep things simple, we'll consider a case of pure bending. A section of a beam is said to be in a state of pure bending when the shear force along it is equal to zero, and so there is a constant bending moment along its length, like there is for this beam loaded by two moments. We also have a case of pure bending over the middle section of this beam, where the bending moment is constant. Let's look at how a beam deflects when it has a constant bending moment along its length. If we imagine the beam as a collection of very small fibers, as the beam deflects, the fibers at the top of the beam get shorter, meaning that they are in compression, and those at the bottom of the beam get longer, so they are in tension. Somewhere between the top and the bottom of the cross section, there will be a surface containing fibers which stay the exact same length. This is called the neutral surface. It passes through the centroid of the cross section. When looking at the beam in two dimensions, we refer to it as the neutral axis. Let's try and quantify the bending stresses that develop within the beam to resist these applied moments. First, let's calculate the strains in the beam. This can be done quite easily just by considering the geometry of the deformation. Let's watch how a fiber at the neutral axis between points A and B and a fiber between points C and D located at a distance y from the neutral axis deform. Since this is a case of pure bending, we can see that the fibers bend into a perfectly circular arc. We'll call the center of the circle O. Before any deformation, the fibers are all the same length. After the deformation, the length of the neutral axis has stayed the same, but the length of the fiber between points C and D has increased. If theta is the angle of the arc and r is the radius of the arc to the neutral axis, we can calculate the length of the arc between A and B, like this, and we can calculate the length of the arc between C and D in the same way. Strain is defined as the change in length divided by the original length, and so we can derive an equation for bending strain at any distance y from the neutral axis. We define the distance y as being positive downwards, and so this equation will give us a positive strain for the bottom of the cross-section, which is in tension. Sometimes you'll see this equation written with a minus sign, but that's because y was defined as being positive upwards. If we assume that stresses remain within the elastic region of the stress-strain curve, we can then apply Hooke's law for uniaxial stress to calculate the bending stresses. This gives us the equation for bending stress as a function of the radius of curvature, r, of the deformation. But what we're really interested in is how the bending moment, m, affects the bending stress. If we make an imaginary cut through the beam, we can expose the internal bending stresses, represented here as a few discrete forces. The resultant moment of these internal forces must be equal to the bending moment m, and so we can calculate m by integration, like this. Now we can plug in the equation for bending stress we just derived. When rearranged into this form, we can notice that the integral on the right is the definition of the area moment of inertia. This parameter, which I've covered in detail in a separate video, defines the resistance of a cross-section to bending due to its shape and is denoted using the letter I. We can combine this equation for the bending moment with the bending stress equation to obtain what is known as the Flexural formula. So what does it tell us? Bending stress increases linearly as the bending moment and the distance from the neutral axis increase, and it decreases as the area moment of inertia increases. The maximum stress occurs at the fibers furthest from the neutral axis. The term I over Y max depends only on the geometry of the cross-section, and so it is called the section modulus, and is denoted using the letter S. You will often see the section modulus listed for a range of common beam cross-sections in reference texts. The I-beam is a commonly used cross-section because it has a large area moment of inertia, which results in lower stresses. Here's how the bending stresses are distributed over an I-beam cross-section. They are zero at the neutral axis and reach a maximum at the outside surfaces of the flanges. For a T-section, the neutral axis is shifted upwards, and so the bending stress distribution looks like this. So we've established how to calculate the bending stresses, which are normal stresses, for a case of pure bending. Most of the time, we won't have pure bending, as there will also be a shear force acting on the beam cross-section, like the beam we saw at the start of the video. It turns out that the presence of a shear force doesn't normally significantly affect the bending stresses, and so, luckily, we can consider the Flexural formula we derived earlier for pure bending to be valid for a more general case of bending. The shear force V is the resultant of shear stresses, which act vertically, parallel to the cross-section. We denote the shear stresses using the Greek letter tau. To maintain equilibrium, these vertical shear stresses have complementary horizontal shear stresses, which act between horizontal layers of the beam. One way to visualize these horizontal stresses is to consider a beam made up of several planks of wood. When a load is applied, there is a tendency for the planks to slide relative to one another. Now let's glue the planks together. When the load is applied, the planks cannot slide, and so horizontal stresses develop between them. If these shear stresses are larger than the shear strength of the glue bond, the glue will fail. These horizontal shear stresses don't exist if we apply a moment instead of a force, because that gives us a state of pure bending, and so there is no tendency for the planks to slide relative to one another. The presence of these horizontal shear stresses explains why wooden beams sometimes fail by splitting longitudinally. This failure usually occurs close to the neutral axis, for reasons which will soon be obvious. So how can we calculate the shear stresses? We can calculate the average shear stress acting on the cross-section as the shear force V divided by the cross-sectional area. But the shear stresses aren't distributed uniformly across the beam cross-section. The shear stress has to be zero at the free surfaces at the top and bottom of the beam. So the average shear stress isn't very useful, since it doesn't tell us the maximum shear stress. Instead, we can use this equation to calculate the shear stresses acting on the cross-section. I won't cover the derivation of the equation here, but it's based on considering equilibrium of stresses acting on a small element within the beam. The equation assumes that the shear stress is constant across the width b of the cross-section, so tau is a function of the distance along the beam, x, and the distance above the neutral axis, y. V is the shear force acting on the cross-section, which varies with the distance along the beam. B is the width of the cross-section. It can vary with the distance y from the neutral axis, but in this case, the cross-section is rectangular, so B is constant. I is the area moment of inertia, which is a constant value calculated based on the shape of the cross-section. And Q is the first moment of area for the portion of the cross-section above the location we want to calculate the shear stress for. So it varies with the distance y above or below the neutral axis. It is equal to the product of the area above the location of interest and the distance between the centroid of that area and the neutral axis. If the location of interest is below the neutral axis, we consider the area below the axis instead of the area above it. To calculate the first moment of area at this line, which is at a distance y from the neutral axis, we multiply the area of the blue rectangle above the line by the distance from the neutral axis to the centroid. Doing this calculation gives us an equation for Q as a function of the distance y from the neutral axis for a rectangular cross-section. And so we can obtain an equation which describes how the shear stress varies with distance from the neutral axis. The y term is squared, and so the shear stress varies parabolically over the height of the cross-section, with the maximum shear stress occurring at the neutral axis. This is opposite to the bending stress, which is zero at the neutral axis, and explains why the horizontal shear failure of a wooden beam we saw earlier occurs close to the neutral axis. By setting y to zero in this equation, we obtain an equation for the maximum shear stress in rectangular cross-sections. It is equal to 1.5 times the average shear stress across the entire cross-section. The derivation of this equation for shear stress makes a few assumptions, so we need to be careful with how we apply it. First, it assumes that the shear stresses are constant across the width of the cross-section. For rectangular cross-sections, this is a reasonable assumption if the rectangle is thin. But for cross-sections like this one, the shear stresses can vary significantly over the width. And so, in these cases, the equation can really only give us the average shear stress across the width of the cross-section. It can't tell us what the maximum shear stress will be. Another assumption this equation makes is that the shear stresses are aligned with the y-axis. Shear stresses act tangentially at a free surface, so for a circular cross-section, for example, we can't strictly use this equation to get the distribution of shear stresses across the height of the cross-section, but we can still use it to estimate the shear stresses at the neutral axis, because the shear stresses there are aligned with the y-axis. The equation for shear stress at the neutral axis in a circular cross-section is similar to the equation for a rectangular section, where we have the average shear stress V over A multiplied by a constant. The constant is 4 over 3 for a circular cross-section and 3 over 2 for a rectangular one. We can also use the shear stress equation for thin-walled sections like this I-beam, although things are a bit more complicated. Because the vertical shear stresses at the surfaces shown in red must be 0, and because the flanges are very wide, the vertical shear stress in the flanges is very small. This means that the vertical shear stress is distributed like this. The web mostly carries the shear force, and the flanges mostly carry the bending moment, as we saw earlier. You can see that the shear stresses are distributed quite evenly over the height of the web. This is because the flanges contribute significantly to the first moment of area Q when calculating the shear stresses in the web, but they don't carry much of the vertical shear force. Since the web is thin, the shear stresses are also distributed evenly across its width. Because of this, we can easily calculate the approximate shear stress in the web, like this. More detailed analysis reveals that there are shear stresses in the flanges, but they are acting mainly in the horizontal direction. The horizontal stresses on both sides of the flanges cancel each other out, so the net shear force is still just a vertical force. We can figure out the direction of the horizontal shear stresses based on the direction of the vertical shear stresses by imagining that the stresses are flowing through the cross-section. That's it for this review of bending and shear stresses in beams. If you enjoyed the video and would like to see more content like this, please consider supporting the channel on Patreon. Thanks for watching.
Hello guys, welcome back to the Civil Engineering YouTube channel. Please subscribe our channel for the Civil Engineering video. Today our lecture is about the flexural stresses. The flexural stresses, also known as the bending stresses. Bending stresses. We can say that these are the stresses occurring from the bending of any structural member, and these stresses are mostly common occurring in the beams and the slab and also in the retaining wall. Mostly design these three members for the flexural stresses. Retaining wall. So why these stresses occur in this member? Because if I consider the simple example of this beam, let's consider this simple example of simply supported beam with a uniformly distributed load acting on this beam is let you. So upon loading, this beam will start deflection and it will be resisted. At the two supports, there is no deflection in the supports. So due to this deflection, due to this bending, the stresses will occur in this beam, which is known as the flexural stresses or bending stresses. So all these three types of the structural member are mostly dominant in the flexure. They don't have any axial stressing. Like if I consider the column is mostly dominant in the axial. So when the load acts on the column, so the load acts through the axis of the column, they mainly have axial stresses in the column, while beam, slab, and retaining wall are mostly designed for the flexural stresses. That's why the design process for these three types of structural member will be called as the flexural design. So due to this deflection, we hope the flexural stresses are depending stresses throughout the length of the beam. In this portion, you can see that there will be less flexural stresses and here increasing, and the maximum flexural stresses will occur at the middle of the beam. And here also increasing, and the maximum flexural stresses at the middle of the beam. So if I consider the cross section of the beam, let's consider this cross section of this beam, where this is the width of the beam is H, this width of the beam is B. So if I draw the cross section, this is stress diagram for this beam. So there will be two types of the stresses. The flexural stresses are classified, you can say, into two types. One is the compressor stresses, and one is the tension stresses. So the beam will be subjected to the compressor stresses at the top. Compressor stresses, this beam will be compressed at the top, and will be tension at the bottom. Tension stress at the bottom. So that's why the flexural stresses has two main categories of compressor stresses and the tensile stresses or tension stresses. While at the neutral axis we have zero stresses. This is called as the neutral axis. And we can find out the flexural stresses by this formula. The flexural stresses are bending stresses equal to the Ny divided by I, where N is the moment demand, at which point you are interested to find the moment. Flexural stresses, so you will put the moment value. Like let's suppose I'm interested to find the flexural stresses at this portion, right? So I will find out the moment value at this point. The Y is the distance from the neutral axis up to which in which you are interested to find the flexural stresses from the depth of your beam. Let's suppose this is your Y on the neutral axis. If you are interested to find the stresses at the top of the beam, which is the maximum stresses, it will be called as the C. This formula can be updated is like this way: MC over I, where C is now called the maximum distance from the neutral axis to the point of interest, while the I is the moment of inertia for this beam. If you can see here, there is a rectangular beam. The moment of inertia for a rectangular beam will be Ph3 over 12. So by putting all this value into this equation, you can find the flexural stresses of your beam, which will be maximum at the top and the bottom, compressive and tension. So this was all about the flexural stresses. These are mostly common occurring in the beam, slab, and retaining wall, and they must be designed for the flexural stresses, and we provide the bottom of the beam for tension. So the concrete is weak in tension, while the compressor stresses we don't put in reinforcement, but the concrete is strong with compression. So concrete is okay for the compression stresses. This was all about the flexural stresses. Hope you guys understand how we find the flexural stresses and what is the flexural stresses.